welcome back to the course on computer network and internet protocols. So, we are looking into the transmission control protocols in detail. So, in the last class we have looked into the flow control algorithms in TCP. So, in this lecture we will look into the congestion control algorithms in TCP. In the context of generic transport layer protocols, we have looked into that this congestion control algorithms in a transport layer, they use a nice principle to ensure both efficiency as well as fairness. So, here we will look into that how TCP utilizes the concept of capacity and fairness together in the congestion control algorithm which it incorporated. So, here is the basic congestion control algorithm for TCP. So, the basic congestion control algorithm for TCP is based on the implementation of additive increase, multiplicative decrease using a window based control mechanism, and TCP considers packet loss as a notion of congestion. Earlier we have looked into these principles of additive increase, multiplicative decrease, where we have seen that AIMD provides a notion of maximizing the capacity as well as fairness in the network. So, what we have looked into that whenever there are multiple flows which are getting congested at the network bottleneck or at the bottleneck link, both the flows are trying to maximize their capacity, and when both the flows tries to maximize their capacity, during that time we need to ensure that every flow gets the required capacity that maximizes its fairness as well. So, considering the global network perspective where multiple flows are contending with each other to get the information, to get the data, during that time this notion of congestion and the notion of fairness in congestion is an important aspect. And what we have seen earlier, that in case of a distributed network, ensuring hard fairness is very difficult, and at the same time hard fairness can affect your capacity, the available capacity, or it can underutilize the available network capacity. So, to remove the underutilization of the network capacity, that in network generally we use the max min fairness principle, and the max min fairness principle says that your objective would be to maximize the end to end capacity that you can get for a particular flow. In that notion, we have seen that AIMD provides this max min fairness along with maximizing the utilization of the link bandwidth that you have at the network bottleneck, in contrast to additive increase, additive decrease principle of rate control and multiplicative increase, multiplicative decrease notion of rate control. So, TCP incorporates the same principle of additive increase, multiplicative decrease, where it increases the rate additively whenever there is sufficient amount of bandwidth available in the end to end path, and whenever TCP detects a congestion with the help of a packet loss, where packet loss gives a signal to congestion, then it drops the rate in a multiplicative way or following a multiplicative notion. So, this AIMD principle that we discussed earlier is incorporated in TCP. So, to incorporate this notion of AIMD for congestion control while maintaining fairness, TCP maintains a window which is called the congestion window. So, this congestion window is the number of bytes that the sender may have in the network at any instance of time. Now, if that is the case, then your sending rate will be equal to the congestion window divided by RTT. So, RTT is the round trip time, the time to propagate a message from one node to another node and then getting back the reply, this total round trip time. So, if you divide the congestion window size, that means the number of bit or the number of bytes that the system can push to the network divided by the total RTT, that gives you an approximation of the sending rate, when the sender is sending data at a rate of congestion. But as we have seen earlier, we have another notion here which is the receiver window size or the rate of the receiver, which comes from the flow control algorithm. So, ideally what we have to do, we have to incorporate or we have to merge the flow control principle along with the congestion control principle. And what we have seen earlier, that the flow control, it maintain its own window size which is based on the feedback of receiver advertised to window. So, the receiver advertised to window, receiver announces that that is the available place or the available buffer at the receiver. So, the sender can send that much amount of data, so that buffer overflow does not occur from the receiver side, and with that from this receiver feedback window size, the sender also controls its rate. So, ideally your sending rate should be the minimum of the receiver rate, the rate at which the receiver can receive the packet, and the rate at which the network can deliver the packet to the other end. So, that is why your sending rate should be minimum of the receiver rate and the network supported rate. Now, this concept of network supported rate, it is coming from the congestion control algorithm, and the receiver rate, that is coming from the flow control algorithm. Now, the receiver advertised window size, that gives you the possible rate at which the receiver can receive the data, and the congestion window size, that is giving the rate at which the network can support transmission of data over the end-to-end links. So, that way your sender window size should be the minimum of congestion window and the receiver window. So, this congestion window is providing you the rate that network supports, and receiver window is giving you the rate that receiver supports. So, that way, and as we are getting the sender window, that is giving you the sending rate or the sender rate. So, this is the notion of combining congestion control and flow control together in TCP, and with this principle TCP controls the sender window size. So, initially your congestion window size is kept at a very minimal rate, then we increase the congestion window size gradually to find out that what is the bottleneck or what is the capacity of the link, and if a congestion is detected, then we apply the AIMD principle to decrease the rate. So, that is the broad idea of congestion control in TCP. Now, let us see that how this entire congestion control in TCP was invented, and this congestion control in TCP is a nice example of a networking, or a better to say a decentralized or distributed networking protocol. So, this entire concept of congestion came in 1986 from an event called congestion collapse. So, in 1986 this growing popularity of internet, it led to the first occurrence of congestion in the network. So, we call it as the congestion collapse. So, this congestion collapse was a prolonged period during which the output of the system that they dropped significantly, more than a factor of 100. So, based on this notion of congestion collapse or the observation of congestion collapse, Van Jacobson was the key person who actually investigated this phenomena of congestion in the internet, and this early TCP congestion control algorithm that was developed by Van Jacobson, and the initial proposal came around 1988, which was successor of the event of congestion collapse that happened in 1986. But the challenge for Jacobson was to implement the congestion control algorithm without making much changes in the protocol. It was necessary to make the protocol instantly deployable in the network, because during that time many of the systems were using TCP for transmission of data, and the notion of internet was already there. People were accessing data over the internet. So, during that time if you design a completely different protocol, what you have to do? You have to make the change to all the machines in the system, and during that time the size of the network may not be as large as it is today, or maybe some 1000 factors lesser than today, but still it was significant, and design of a complete new protocol may lead to a problem of backward compatibility. So, that was the major challenge for Jacobson, to design a new protocol which would be compatible with the existing implementation of TCP, and you do not require much changes in the TCP protocol. So, to solve this, Jacobson had a nice observation, and the observation was that he found that well, packet loss is a suitable notion for congestion. Now, here there is a glitch. Remember that during that time when Jacobson invented this congestion control algorithm in TCP, the notion of wireless network was not that much popular, or it was just in a very nascent stage. So, most of the internet was connected by the wired network, and in a wired network in general you do not get a loss from the channel, because the communication media is guided, it is wired. So, your link layer protocol will take care of the interference in the channel, and that is why you will not experience a loss from the channel. So, your channels are kind of lossless in case of a wired network. So, if there is a loss of packet, that loss is certainly from the network buffers from the intermediate network devices. And because of that, if there is a packet loss from the network buffer, you can certainly infer that the buffer has overflown, and because the buffer has overflown, you are having a congestion in the network. So, because of the congestion, the buffer can only overflow. So, that way Jacobson found out that the packet loss is a suitable signal for congestion. So, you can use the timeout to detect the packet loss and then tune the congestion window based on the observation from packet loss. So, you increase the congestion window value, the moment you observe a packet loss, that it gives you an indication that well, there is a notion of congestion in the network, or there is some occurrences of congestion in the network because of which the packet has lost, which you have detected from a timeout. And whenever you are detecting a packet loss from a timeout, then you apply IMD principle to reduce your rate based on the multiplicative decrease principle. Well, so here is the another interesting observation, that how will you adjust the congestion window based on the IMD principle. So, one of the most interesting ideas in TCP congestion control is use of acknowledgement for clocking. So, here this picture depicts the interesting fact that well, whenever you are sending the packet, so assume that this is a network scenario, you have the sender and an intermediate router and then the receiver, they are connected via two links. So, it is a two-hop path. So, this link is a fast link. So, this is a fast link and the second link is a slow link. So, this second link is basically your bottleneck link. So, the congestion will happen when lots of data will be pushed to the slower link or the bottleneck link. Now, whenever you are sending the packet, so you are sending the packet from the sender in the form of a burst that traverses the faster link. Then in the slower link, because this link is slower, your packet will take more time to propagate to the receiver. Now, when if you look into the acknowledgement, the rate of the acknowledgement will actually be the rate of sending the packet at this slower link. So, whatever be the rate of acknowledgement at this slower link, the same rate of acknowledgement will perceive in this fast link as well. So, that way whenever the sender will get the acknowledgements, that acknowledgement actually indicates the rate of the slower link which is there in your end-to-end path, or better to say, if you have multiple hop path, then the rate of the slowest link. In that rate, the acknowledgement will arrive at the sender. Now, if sender monitors the rate of acknowledgement, that gives an idea that well, possibly at that rate the packets are being transmitted to the receiver. So, the acknowledgement returns to the center at about the rate that the packets can be sent over the slowest link in the path. So, you trigger the congestion window adjustment based on the rate at which acknowledgement are received. So, here these acknowledgements are used as a clocks to trigger the congestion control in the network. So, that was another interesting observation by Jacobson while designing the congestion control algorithm. So, well, that was the basic principle. Now, whenever you are getting an acknowledgement, you will trigger or you will adjust your congestion window size, but the question comes that at what rate you will apply additive increase in the network. So, initially what you can do that you can set the congestion window to 1 packet and then gradually increase the size of the congestion window when you will receive an acknowledgement. Now, let us see what happens if you apply a additive increase principle. So, if you apply a additive increase principle, what additive increase says that initially you send one packet, whenever you are making an acknowledgement, then you increase the congestion window by 1. So, now your congestion window is 2. So, you send 2 packets. So, once you are successfully receiving that 2 packets, the acknowledgement for those 2 packets, then again you increase your congestion window by 1. So, now your congestion window is 3. So, you can successfully transfer 3 packets. You wait for the acknowledgement for those 3 packets. So, whenever you are receiving the acknowledgement for those 3 packets, again you increase the congestion window to 4 from 3 and send 4 packets. Now, if you are applying this additive increase of congestion window over the network, so this AIMD rule, it will take a very long time to reach a good operating point on fast networks, because this congestion window is started from the small size. So, let us see an example. So, assume that you have a 10 Mbps link, with 100 millisecond of round trip time, and in that case your appropriate congestion window size should be equal to BDP, the bandwidth delay product that we have seen earlier. So, with 10 Mbps link and 100 millisecond RTT, your bandwidth delay product comes to be 1 megabit. Now, assume that you have a 1250 byte packets. You have a 1250 byte packets means you have 1250 into 8. So, that means 10,000 bits packet, and if you have a 10,000 bit bit packet. So, if you have a 10,000 bit packet, that means with 1 megabit BDP, you need to transfer at least 100 packets to reach to the bandwidth delay product. Now, if you assume that the congestion window starts at 1 packet and the value of the congestion window is increased 1 packet at every RTT, because this RTT is based on the rate at which you are receiving the acknowledgement. So, at every RTT you increase 1 congestion window. So, you require 100 RTTs, and 100 RTTs means with 100 millisecond per RTT, it is approximately 10 seconds before the connection reaches to a moderate rate, or it reaches to its maximum capacity. Now, if you think about the wave transfer, the HTTP protocol. So, none of the HTTP connection takes 10 seconds to reach at that operating point. By the time you will reach at the maximum capacity, you will probably close the TCP connection and start again a new connection, which will again increase from 1 packet per second. Now, to increase this rate, we apply a principle in TCP which is called slow start. So, what is this slow start? So, the slow start is something like this, that initially you make a exponential increase of the rate to avoid the slow convergence. Now, this is an irony in the name, that slow start does not mean that your rate is slow. It is just like that, you are starting from a slower rate and making a faster convergence to the high rate. So, what we do at slow start, we increase the congestion window by 2, that means the congestion window is doubled up at every RTT. So, rather than have an additive increase, initially we do a multiplicative increase by doubling up the congestion window at every round trip time. So, that is the notion of TCP slow start, that every acknowledgement segment allows 2 more segments to be sent. So, for each segment that is acknowledged before the retransmission timer goes off, the sender adds 1 segment out of bytes to the congestion window. So, what happens here with this example? So, initially your congestion window was 1, once you are receiving the acknowledgement, your congestion window becomes 2, that means 2 into 1. Once you are receiving the second acknowledgements, your congestion window becomes 4. Then once you are receiving all these 4 acknowledgements, your congestion window becomes 8. So, that way at every RTT, and all of this transmission takes around 1 RTT. In the first RTT, you are acknowledging 1 packet, in the second RTT, you are acknowledging 2 packets, in the third RTT, you are acknowledging 4 packets, in the fourth RTT, you are acknowledging 4 packets, and if the pipe is full, then that is the level at which you are getting converged. So, that way in TCP slow start, at every round trip time, we double up the congestion window size. Okay. Now, if you just make a multiplicative increase of congestion window, then again it violates the principle of max-min fairness that we have seen earlier. So, MIMD multiplicative increase, multiplicative decrease does not lead you to a optimal operating point where both the capacity and fairness constraints are satisfied. So, that is why what we have to do, we have to make a additive increase at some point of time. So, what we do here? So, the slow start, it causes the exponential growth. So, eventually it will send too many of packets into the network too quickly. Now, to keep the slow start under control, the sender keeps a threshold for the connection. We call this threshold as the slow start threshold or SS stress. Now, initially this slow start threshold is set to BDP or some value which is arbitrarily high, the maximum data flow can push to the network, and whenever a packet loss is detected by a retransmission timeout, the slow start threshold is set to be half of the current congestion window. So, so that is the idea. So, whenever your, so let me try to explain it with a diagram. So, initially these things happen. So, at this axis I have the time, and at this axis I am plotting say the congestion window. So, you start with one packet, and initially you have a exponential growth, and say at this point you get a loss or a retransmission timeout, and whenever you are having a retransmission timeout, so you set, so this was the initial value. So, you set half of that as the slow start threshold. So, you drop the rate and now your slow start threshold is here. So, again you start with one congestion window. So, you go exponentially up to this slow start threshold. After you have reached slow start threshold, you increase through AIMD. So, here your AIMD starts. Now, again after AIMD at this point, if you have an RTO, then you make half of that at the updated slow start threshold, drop the rate, again make an exponential increase up to slow start threshold and start AIMD after that. So, your slow start is up to the slow start threshold, and after that you are going with AIMD. So, after slow start threshold we move to the additive increase. So, in this additive increase which we call as the congestion avoidance. So, whenever the slow start threshold is crossed, TCP switches from slow start to additive increase. So, it is usually implemented with a partial increase for every segment that is being acknowledged, rather than an increase of one segment part RTT. So, this one segment part RTT is your slow start phase. So, to do that we make a common approximation is to increase the congestion window for additive increase based on this formula. So, the congestion window is increased as the current value of the congestion window plus the maximum segment size into maximum segment size divided by the congestion window. This gives an approximation of the additive increase, that how much data or how much new byte need to be added to the congestion window to follow the or to increase the congestion window value based on additive increase at every round trip time. So, at every round trip time we approximate the increase of congestion window based on this formula. So, this formula is applied at every round trip time to have the congestion window follow the additive increase principle. So, it looks like this in additive increase if you do the packet wise approximation. So, in additive increase initially the say the congestion window was 1, once you are getting an acknowledgement you make the congestion window to 2, then you are getting this 2 acknowledgement you are making congestion window to 3, then in the next RTT you are getting the acknowledgement for those 3 packets. So, you are making congestion window to 4. So, this additive increase we approximate based on the formula that we have given earlier. So, that is the broad idea. So, of increasing the congestion window by using the additive increase principle. Okay. So, so to trigger a congestion, as we have mentioned that we normally trigger a congestion with the help of a retransmission timeout that indicates a packet loss, but there is another way to trigger the congestion. So, in general TCP follows two different ways to trigger a congestion. One is the retransmission timeout and the second one is by using a duplicate acknowledgement. So, duplicate acknowledgement means you are continuously receiving the acknowledgement of the same packet. Now, why we use basically the duplicate acknowledgement to trigger a congestion control? Because if you use retransmission timeout, you have to wait for that timeout duration to detect a congestion, whereas duplicate acknowledgement gives you a early notion of congestion and you can trigger the congestion control behavior much earlier compared to waiting for a complete timeout period. Now, interestingly, this retransmission timeout RTO is a sure indication of congestion, but it is time consuming, whereas this duplicate acknowledgement here, as we know that the receiver sends a duplicate acknowledgement when it receives out of order segment, which is a loose way of indicating a congestion. So, TCP assumes that if you are receiving 3 duplicate acknowledgements, then it implies that the packet has been lost and it triggers a congestion control mechanism. Now, this assumption of 3 duplicate acknowledgement is something arbitrary. There is as such no logic behind that. So, Jacobson assumed that well we can take 3 triple duplicate acknowledgement to indicate a congestion. Another important or interesting observation from this duplicate acknowledgement is that because TCP uses cumulative acknowledgement, by looking into the duplicate acknowledgement, you can identify the lost packet, that which packet has been lost. So, the very next packet in the sequence that have been lost. So, that is why you are getting this duplicate acknowledgement. So, what may happen, say you have received 1, 2, 3, then you have lost packet 4 and you are receiving 5, 6, 7. Whenever you are receiving 5, 6, 7, you will receive an acknowledgement up to 3. So, every time you will receive a duplicate act for act 3. Now, in this case you can infer that the packet 3 is actually the packet that has been lost. So, you retransmit the lost packet and then trigger the congestion control algorithm. So, this concept is known as fast retransmission, which is incorporated in one variant of TCP congestion control, which is called TCP Tohoe. So, in TCP Tohoe we use 3 duplicate acknowledgement as the sign of congestion. So, once you receive 3 duplicate acknowledgement, you retransmit the lost packet, that is the fast retransmission, because you can infer the identity of that lost packet. It takes 1 round trip time. Then you set the slow start threshold as half of the current congestion window and set the congestion window to 1 MSS. So, that is the idea of TCP Tohoe. So, initially you have the slow start phase. So, you reach the slow start threshold. Once you are reaching the slow start threshold, you are applying additive increase. At this point, you have detected a congestion by say packet loss. Whenever you are detecting a congestion, you drop the packet, again increase and make the threshold to half of the current slow start threshold. So, earlier your current congestion window. So, your current congestion window is 40. So, you make the threshold as 20 and have slow start up to that threshold. Now, in TCP Reno there is another interesting observation from the implementation of TCP Reno. So, once you are detecting a congestion through 3 duplicate acknowledgement, do TCP really need to set congestion window to 1 MSS? Now, here this duplicate acknowledgement, it means that some segments are still flowing in the network. It is not like that you are not able to send any packet. So, if you are having a retransmission timeout, that means you are not receiving any acknowledgement, but whenever you are receiving some acknowledgement, that means possibly that packet, say in the earlier example that I was showing, possibly packet 3 has been, say packet 4 has been lost, but the receiver is receiving packet 5, 6 and 7. So, when the receiver is receiving packet 5, 6 and 7, it is sending back a duplicate acknowledgement. So, that means you have lost, possibly lost packet 3, but it is not like that. This the link is entirely getting choked, some packets are still flowing in the network. So, that is why the congestion is not that much severe. So, you do not need to reduce the congestion window again at 1 MSS and start the slow start again. So, what we do here? You immediately transmit the loss segment that we call as the fast retransmit, and then transmit additional segment based on the duplicate acknowledgement that has been received. We call this concept as the fast recovery. So, what happens in fast recovery? That you set the slow start threshold to 1/2 of the current congestion window, retransmit the missing segment, that is the fast retransmit. Then you set the slow start threshold to the current, then you set the congestion window to the current slow start threshold plus 3. Why 3? Because you have received 3 duplicate acknowledgement, that means the receiver has already received 3 more packets. So, that means you can increase the congestion window and send 3 more packets to the network, because that has been received by the receiver, although out of order. So, each time you receive another duplicate acknowledgement, you set the congestion window to congestion window plus 1, you increase the congestion window value. Then send a new data segment if allowed by the current value of the congestion window. So, that way whenever you are receiving the duplicate acknowledgements, you are gradually increasing the congestion window value and sending more packet to the network. So, that we call as the fast recovery, and the fast recovery ensures that because some packets are flowing in the network, you do not need to again wait for sending the data at a very low rate. So, once you receive a new acknowledgement, so you are receiving a new acknowledgement because you have retransmitted the loss segment in fast retransmit. So, that loss segment, if it reached at the receiver, so in that earlier example, say 4 has been lost, the receiver has received 5, 6, say 7, 8, 9, and here you have received 3 duplicate acknowledgement corresponds to 5, 6, 7, and at that time the sender has retransmitted segment 4 and it was receiving this 8 and 9 duplicate acknowledgement corresponds to that, and with every duplicate acknowledgement you keep on sending the further packets. And whenever the receiver received this missing 4, during that time the receiver sends a cumulative acknowledgement, say ACK 11. And once you are receiving this new acknowledgement, not a duplicate acknowledgement, that means all the packets that was there that have been acknowledged. So, at this stage you exit from the fast recovery. So, this causes setting the congestion window to the slow start threshold as we have done earlier, and continue with the linear increasing due to the congestion avoidance algorithm. So, this is the idea of fast recovery that has been incorporated in TCP Reno, the next version of TCP Tohoe. So, in fast recovery what we do, initially you apply slow start up to slow start threshold, then you go for additive increase. At this stage you have detected a packet loss through triple duplicate acknowledgement. Whenever you are detecting a packet loss through 3 duplicate acknowledgement, you reduce the congestion window value to the updated slow start threshold, that is half of the current slow start, and apply fast recovery at that point. So, after applying fast recovery, whenever you are receiving a new acknowledgement, again you go with the additive increase. So, here if you compare it with the TCP Reno variant, we are not making the congestion window. So, TCP Reno, it make the congestion window again to 1 MSS and then apply slow start threshold up to slow start up to the slow start threshold, and then applies the additive increase. So, here we are applying additive increase much faster, that will help you to reach to the operating point at much faster compared to TCP Reno, due to the implication of this fast recovery algorithm and avoiding the slow start phase again whenever you are detecting a congestion through the triple duplicate acknowledgement. But if you are detecting a congestion by a retransmission timeout, then you always set the congestion window to 1 MSS and start with the slow start threshold, because start with the slow start phase, because a retransmission timeout will give you an indication that a severe congestion has been happened, and whenever there is a severe congestion in the network, it is always better to start with a very low rate, that means setting the congestion window value to 1 MSS. So, that is the broad difference. So, if you are detecting the congestion by a retransmission timeout, you set the congestion window value to 1 MSS, apply the slow start. Whenever you will reach the current slow start value, which is the half of the congestion window that was detected during the congestion detection, and then apply additive increase. And if you are detecting a congestion through triple duplicate acknowledgement, you do not need to again perform the slow start phase, because some packet are still flowing in the network. You directly apply fast recovery and then move with the additive increase. So, this is the variant of the TCP Reno. After that, many other variants of TCP came into existence, like TCP New Reno, then TCP Selective Acknowledgement or SAC. So, originally the normal TCP protocol, it uses the principle of go back in flow control principles or go back in ARQ principle, whereas the TCP SAC, the selective acknowledgement variant of TCP, it works in the principle of this selective repeat ARQ, where explicitly we send the SAC packet to indicate that which packet has been lost, and the sender retransmit that packets without sending the whole packet of the current window. So, there are lots of such variants of TCP, and after that many of the variants also came into practice. So, I am not going to the details of all those variants. If you are interested, you can go with that. The basic notion of TCP congestion control is these 3 phases: the slow start followed by the congestion avoidance, then the fast recovery and the fast retransmit. And after that, people have incorporated few other optimizations. So, if you are interested, you can look into the RFCs to know them in better. So, this gives us a broad overview of the congestion control algorithms which are there in TCP, and we have given you a fairly detailed description of the transport layer protocol along with a focus on this TCP. So, as I have mentioned that a huge amount or even more than 90% of the internet traffic, it actually uses TCP protocol, and TCP is possibly the most widely deployed protocol in internet, the transport layer protocol in internet. But well, there are certain applications in the internet that use UDP, which does not support reliability, flow control, congestion control as like TCP. So, in the next class, we will look into the details of the UDP protocol. So, thank you all for attending this class. See you again.